Welcome back to Mutlu Learning Hub. Today we are going to talk about the error matrix. Here is the thing, every model makes mistakes, so the real question we'll answer today is which mistakes matter most for your model. Last time we talked about R squared and adjusted R squared metrics that tell us how much of the variation in the data the model explains. But they don't tell us how big are the mistakes the model is making. That's where error matrix come in. These focus not on variation but on the size of the prediction errors. Remember that the error is the difference between the actual value and the predicted value. And on the graph, you can see that, for example, for this point, the error is this distance. Error matrix quantify how far predictions are from actual values. But here is the twist. Not all error metrics treat mistakes the same way. Some treat all mistakes equally, others crush big mistakes much harder, and it matters which one you choose. There are three main error metrics: mean absolute error, mean squared error, and root mean squared error. Mean absolute error is the simplest. It measures how far off we are on average. Let's look at the formula. Here n is the number of points, yi is the actual value, and yi hat is the predicted value, and this is the error. So mean absolute error measures the average absolute distance between prediction and the actual value. You can use it when each error should count equally. Here is a tiny example. Here we have the predicted values and actual values, and we have 3 data points. Let's calculate the error. For the first data point, we have 10 minus 11, the absolute value of 10 minus 11. We have 1. For the second data point, we have absolute value of 12 minus 15, so we get 3. And then for the third data point, we have 5. Then we calculate the mean absolute error. Here, the number of points is 3, so we have 1 divided by 3 times 1 plus 3 plus 5. So we get 9 divided by 3, which is 3. So on average, we are off by 3 units. Mean absolute error is nice because it's easy to understand, robust to outliers, and it has the same units as the target. But large errors are not heavily penalized and it's not differentiable at 0. This makes gradient-based optimization harder. Now let's move to mean squared error. Mean squared error takes every error and squares it. So it's the average squared error. If you want bigger mistakes get much bigger penalties, mean squared error is a good choice. And it's the core objective in many models. But the result is in squared units, so it can be unintuitive. Now let's see an example. We already calculated the error, so now let's calculate the mean squared error. We have 3 data points, so again we have 1 over 3, and then 1 to 2, 3 to 2, and 5 to 2. So we get 1 plus 9 plus 25 divided by 3, which is 35 divided by 3, and approximately 11.67. As you see here, the error of 5 explodes into 25. That's the whole point. Mean squared error highlights severe mistakes. Now let's focus on its strengths and weaknesses. It's useful because it penalizes large errors more. Also, since it's differentiable, it's ideal for gradient-based optimization and many machine learning algorithms. Practice, a single outlier can dominate everything. Also, the units become squared, so it's less intuitive. Now let's talk about the root mean squared error. You get the power of mean squared error in interpretable units. Now let's see an example. We've already calculated the mean squared error. It is 11.67. So the root mean squared error is square root of 11.67 and it is approximately 3.41. So it is slightly larger than the mean absolute error. Root mean squared error is great when you want a balance. It's same units as target and penalizes large errors. But it's still sensitive to outliers and it's less intuitive than mean absolute error. When should you use which? Use mean absolute error when you want a simple, robust metric. Use mean squared error when big errors are unacceptable. Use root mean squared error when you want interpretability plus outlier sensitivity. So if outliers matter, use mean squared error or root mean squared error. If robustness matters, use mean absolute error. Now that we know how to measure errors, the next question is, why do these errors happen? Is your model too simple, too complex, or just right? That's where the idea of underfitting and overfitting comes in, and that's what we'll explore next. Thank you so much for watching. If this helped you understand error matrix better, hit like, subscribe, and drop your questions in the comments. See you in the next one.